Warning: this project involves mains electricity. Do not attempt unless you know exactly what you're doing. Safety first. Hey, so you probably already guessed what this is, right? But the why behind it, huh? One fine
Bro,
day.
I need a 5-volt power supply to power this temper motor. Do you have one?
Huh. Yes, man. I do have 5-volt power supply. Just one second. Here, have this.
What is this, bro?
It's an old Nokia power adapter, I just split the end so that we get a 5-volt power supply. That's why.
Okay, cool.
A few minutes later.
Bro, I'm about to do some plastic drilling with this micro drill. I need a 12-volt power supply for this. Do you have one?
Oh, you want 12 volt? Here, one second. Here, take these two.
Why are you giving me two adapters, bro?
Oh, one is of 12 volt 1 amp capacity and the other is of 12 volt 2 amp capacity. That's why.
Why don't we just go ahead and buy a benchtop power supply instead?
Instead of buying it, why don't we make one? Okay. I know what you must be thinking. Great. Just another DIY video of converting an ATX power supply into a benchtop power supply, right? Even I have watched a lot of videos like that. But this is different. We are not just doing a standard conversion today. Oh no. We are going to add challenges. Do you see these knobs here? Can you take a guess on what component is behind these knobs? Drop down in comment below. I'll give you some time. Alright, if you have guessed big rotary potentiometer behind these two knobs, that would make sense for most cells will build, but not for this one. We have done something completely different in this one. See, for a variable voltage and current, I have used a nifty buck boost converter to basically get the output. You see these small screws here? These screws are the ones which will be used to control the variable voltage and current. But these screws are too small and we will be needing a tiny screwdriver like this to control. Now the smart move, like Sorin, DIY electrical nerds, would be to use a big round rotary potentiometer like this. Basically, resolder those tiny potentiometers and rewire it, and that is what will directly be connected to these two knobs. But where's the fun in that, right? Now, the challenge would be to control this minuscule screw with a user-friendly knob directly. How are we going to do that? Well,
Several days later.
after some serious head scratching on how to convert this electrical system to a mechanical system, I have come up with this mechanism. Now, your first thought might be, gears? Why make it so complicated, bruh? That's actually an excellent question. Even my first idea was to directly use a single shaft and connect it onto the screw. But it comes up with these following problems. Problem 1. Lateral movement. Yank the knob accidentally and pop, it slips off the screw. We can add stops, but the screw slot is like half a millimeter thick. It's gonna be really tricky to achieve it using 3D printer. Problem number 2. Size and spacing. I wanted to use a decent size knob, maybe 10 to 15 millimeter diameter, but the adjustment screws are also about 11 millimeters apart. Simple shaft wasn't gonna cut it. That's where the gears come into the picture. They offset the control knobs, increasing the center distance. I used a 2:1 gear ratio. One knob turn is equal to 2 screw turns. Speedy adjustments. The gear engaging the screw doesn't move side to side. It is held in place. And this gear, which is highlighted here, is what will be used to turn the screws on the potentiometer. And also, we have a top plate to it, so there is no more popping off, and provide mounting points to the front panel. Now, the problem is solved with excessive engineering. Next, this handy ATX breakout board plugs right into the 24-pin connector, giving us easy access to this 3.3, 5, 12 and minus 12 volts. Now, some of your viewers might have noticed that there are too many ground pins on this ATX board, but there is just only one ground output on this power supply. Stick around for some time and you will know why. The shocking truth, pun intended. I have also added this voltmeter so that we can check the output voltage and current, and I have this multi-position rotary switch so that we can alter from 3 volt, 5 volt, 12 volt and the variable output. So now by rotating this top knob, we will be able to control the output voltage. And obviously, we can't see the current because there is no load connected to it right now. Earlier, I was telling why there is just only one ground connection, right? Basically, all the ground pins are connected together to this ground collector, and that is basically routed to this voltmeter. So now what happens is we can take output from any of these pins and we will be able to see how much current it has drawn. As you can see, this is the 3.3 volt output, and this is the 5 volt output, and this is the 12 volt output, and this is the minus 12 volt output. Now let's power it. We just gotta plug it here and then turn it on. I am connecting this LED array where this yellow wire is the ground and the green wire is connected to the variable output. Now I tried to alter the voltage, but as you can see, since the current is fixed, we are not able to change the voltage. Now let's change the current by rotating the lower knob, but that is also not making any change. Why? That is because we have increased the current limit, and now when we increase the voltage, the amount of current supplied for that voltage is also increasing. Now if we set the current to, let's say, 1.5 to 1.6 amps, no matter how much I turn, the voltage isn't gonna increase. Now let's try the same by connecting it directly to this 12 volt output. Setting the rotary switch to 12 volt, and yep, now you can see through this pin at 12 volt, the maximum current which it is drawing is 0.28 amps. We can also try connecting it to 5 volt, but nothing is happening just as expected because this array is of higher voltage capacity. Now let's try lighting this LED using the 3.3 volt output. Plugging the banana jack to the ground and another wire to the positive 3.3 volt output. Okay, now let's try to light our LED. Ta-da! It's working. And as you can see, this one LED is drawing somewhere around 0.01 to 0.02 amps. Now let's try running this DC motor. Now running it at 3.3 volt is making it rotate relatively slow. So now let's increase the speed by increasing the voltage. Let's connect it to the 5 volt output and let's see the difference. Changing the rotary switch to 5 volt. Now the motor is spinning relatively faster at a higher voltage. But if you observe, the amount of current drawn is still remaining the same. And finally, if you run it at 12 volt, it is running significantly faster and it is also drawing 0.2 amps, somewhere around the same spectrum. And now comes the enclosure. You may be thinking, what is this crazy design? Why don't you basically 3D print the complete enclosure, right? Well, I could have done that, but I kind of wanted to make it more interesting, I utilized the metal enclosure of the ATX power supply and then I spray painted it matte black, and I have modeled two components. The front panel, which is where all these items, the buck boost converter, the voltmeter, the rotary switch, the ATX power board, and the LED light, we should not forget that. And this is something I'll tell you at the end of the video. Stick around. So all these components are basically connected to this front panel. And to cover the wires, I have designed this top cover. And after cramming everything in, ta-da! This is what we have finally. A working benchtop power supply. But wait. There is one part which I haven't covered it, right? This one. You might be wondering what this one is, right? I'll give you some time. Take a guess. Drop a comment down below. If you have guessed a 12 volt cigarette lighter socket, then bang on, you're accurate. What I'm going to use this for? Subscribe to the channel if you don't want to miss. So that was my journey in building this ATX to benchtop power supply. It had its challenges, its questionable design choices, but it works. I'll catch you with another crazy contraption which comes up in my mind. Until then, stay creative, stay curious, and also don't always take the easy way out. Sometimes the challenging way is more interesting. See ya! Creation created for creators.